Hi there, in our second video here on matrices, we're going to be looking at inverse matrices and solving system equations with matrices. That's going to be the bulk of this video. If we look at the syllabus here, we've talked about adding, subtracting, multiplying. I'm going to talk a little bit about this one here, the algebraic properties of matrix addition and multiplication. Look at some special matrices. And really we're going to be looking at 1.4 here, which is about what the determinant and inverse of a 2 by 2 matrix is, and recognise a singular 2 by 2 matrix. And then we can go ahead and solve big systems of equations in 5 unknowns using matrix algebra. So yeah, a lot to cover here, so let's get into it. Okay, first thing is some definitions here from the syllabus about certain matrices. We talks about the zero matrix. Now, it's not going to surprise you that a 2 by 2 zero matrix looks like that. So one with entries with all zero in it. Okay. Another term that's really important is the term identity matrix. I'll tell you why it's called identity in a second. An identity matrix is a square matrix, so 2 by 2 or 3 by 3, where the leading diagonal has ones and all of the rest of the entries in there are zero. So there's a 2 by 2 identity matrix. There's a 3 by 3 identity matrix. The reason it's called the identity matrix is because if we take any matrix A and multiply it by the identity matrix, we get A again. Or in fact, if we say the identity matrix times by A the other way around, we also get the matrix A. And we're talking about 2 by 2 matrices here, okay? This only works with 2 by 2 matrices. So it's the matrix equivalent of the number 1 in a number system. Something times 1 is equal to x times 1 is equal to x. So in matrices we can't have a number, but the thing that performs the same function is what we call the identity matrix. Okay? So we've talked about in the last video what a row matrix is and what a column matrix is. So we know those definitions here, but there's a few more things I think to mention about matrices and the way they behave. We talked about last time the fact that this is not necessarily this. So it's not commutative. A times B is not necessarily BA. And in fact, understanding how matrices are multiplied together, sometimes you can do A times B and B times A isn't even possible. So even if we've got 2 by 2 matrices, it's certainly not a fact that A times B is equal to B times A. That's important. The other thing is, let's look at some other properties here. So I'll note these down. If we're dealing with algebra, then if we have A times B equals 0, then that means that either A is equal to 0 or B is equal to 0. That's a property that you would have been familiar with for a long time. That is not the case with matrices. You might have two non-zero matrices that multiply together to give you a zero matrix, and neither A nor B are 0. So that property does not work with matrices. That's something to be aware of. Next property. If you have in algebra A times B is equal to A times C, that implies that B must equal C. Let's think about that for a second. I'm going to some basic properties here. Well, that's true. You know, 2 times 3 is equal to 2 times what? Well, it's got to be 3. All right, so that works for numbers. But guess what? Does not necessarily work for matrices. So there's some basic rules that matrices don't abide by. And we kind of need to be aware of those. So let's talk about the inverse of a matrix. The inverse of a matrix is the way that we kind of start solving some equations with matrices. I remember I said to you before that in the last video that there's no such thing as division with matrices. We can't divide by a matrix. That kind of doesn't make sense like it does with numbers. So the way that we get around that is using inverse matrices. So if we have an inverse matrix, the definition of it is if we times a matrix by its inverse, we get the identity matrix. Or the other way around, if we've got the inverse times the original matrix, we get the identity matrix. That's the definition of what an inverse is. Remember, we don't have this idea of a concept of like 1 for our number system. The identity matrix is our equivalent of 1. So that's what the identity matrix is, and it's very, very helpful for this reason. If we have a system of equations, ax equals b, and let's say I want to get x on its own in that equation there. Now I can't divide both sides by a. There's nothing that doesn't exist for matrices. What I can do is pre-multiply both sides by the inverse of a. This gives the identity matrix, and then the identity times by x is just going to be x. So there we go, we've solved that equation now. That's how we would find the matrix for x, is by pre-multiplying both sides by the inverse. So we need to know how to work out inverses, and all of this stuff also just applies for 2 by 2 matrices in this course. Later on you could study 3 by 3, 4 by 4, as you go as big as you want. So working out determinants and inverses just 2 by 2, but our calculator can help us to work out inverses of bigger dimension matrices. So you can see a formula there for the determinant and how to get the inverse. I'm going to take you through it. If we've got a matrix A, B, C, D, here it is here, the determinant of the matrix is the difference between the product of the diagonals of the matrix. So A times D minus B times C is called the determinant. The inverse of a matrix is defined like this. It's 1 over the determinant. If our original matrix was A, B, C, D, that's our original matrix, A, B, C, D, as we see there. The inverse, what we do is we swap A and D around. So D goes there, and A goes there, and we change the sign of those numbers there on the other diagonal. That is the formula for the inverse of a 2 by 2 matrix. Let's do some work on this. Okay, so example 4 here, A plus B, well that's dead easy, I'm not going to do that, we did that in the last video. The determinant of A, I'll use these modular signs. We sometimes write it like this, det A, something like that. So in this case, it's 3 times 1 minus negative 1 times 2. The difference between the product of the diagonals. So in this case, 3 plus 2 is 5. So the determinant of this matrix 5. C, to get the inverse now. The inverse of that matrix is 1 over 5. Looking at A at the top there, we swap the 1 and the 3. We change the sign of those other 2's there. There is the inverse of that matrix A. Now you can write that as 1/5, 1/5, negative 2/5, 3/5 if you want. Expand the brackets. Or you could write it as a fraction as well, either way. This one here is perfectly acceptable though. You can certainly write it like that. Okay. So have a go at doing the inverse of matrix B. One thing to note when we're doing these inverse matrices is this. What happens if the determinant is 0? Well, then our formula fails. Okay, we've got 1 over the determinant, and then I'm saying we're swapping these and swapping those. You can see if we get 0 here, we're in problems. Okay, so that is a way that we can tell if a matrix inverse does not exist if the determinant is 0. Okay, does not exist if the determinant of A equals 0. We call these matrices singular matrices, matrices that do not have an inverse. And that's up here. Just highlight this. Any matrix with a determinant of 0 has no inverse. Such matrices are said to be called singular matrices. Okay, so let's do the rest of this question here. The matrix C such that A times C is equal to B. Alright, so this is part B. A times C is equal to B. Right. So again, we want to get C on its own. We can't divide by A. That does not make sense. What we need to do is this. And notice the order is really important here. We can't, if we put A to the minus 1 at the front of both sides, it needs to be the front on both sides, not in the front on one side and at the end on one side, because the inverse of A times B and B times the inverse of A are two different matrices. So we've got to get the order correct here. So on the left-hand side, we get C is equal to the inverse of A times by B. So we have the inverse of A. That's the one that we worked out up here. And we know the matrix B in the question is 3, 4, 2, 1. Okay, so what you can do here is multiply the two matrices. So what you can do here is multiply the two matrices first, then times by 1/5. We'll go a fifth of the first one, then times by the second one. I think the easiest way is to multiply the two matrices first. So let's just recall how to do that. 1 and 1, turn it on its side, move it across. So we get 3 plus 2. Do that again for the 4 plus 1, gives us 5 on the top. Then take the bottom row, turn it on its side and move it across. So we've got negative 2 times 3 plus 3 times 2. So that is 0. Same thing, negative 2 times 4 plus 3 times 1. So negative 8 plus 3 is negative 5. So we end up with 1, 1, 0, negative 1. That's the matrix C. Let's have a look at this example now that has some matrix algebra involved in there. It says matrices P, Q, and R are all 2 by 2 matrices, and R is equal to P minus QR. R is P minus QR. If we assume that I plus Q to the minus 1 exists, prove that R is equal to that, where I is a 2 by 2 identity matrix. Okay, so we're going to do some algebra here. Looking at this the first time, you'll probably think, how the heck are we going to do this? But after a while, you'll get the hang of it. Basically, you need to not break the matrix rules with inverses and dividing. You can't do that kind of thing. So let me show you how this one's done. Firstly, I can see in the thing we're trying to get to, we've just got R on its own. So we've got 2 R's in this expression here, so I'm going to get them all together. So if I add QR to both sides, that doesn't break any matrix rules. Okay? So we can add a matrix to both sides of an equation. As long as they're all 2 by 2 matrices, they're the same order, doesn't break any rules, so that's okay. Now on the left-hand side, I can do this. Factorize. Now, that's what we'd write if we were just dealing with normal variables. Now, there's no such thing as 1 in matrices, but there is the identity. R times the identity matrix is R, and R times Q is QR. Now, the problem with what I've drawn right there is it's wrong. Now the reason is, if we expand this, we get R times R, which is R times Q, which is RQ, but we want QR. That's why it's really important that you do this the right way. So I'm going to write it like this: I plus Q and R at the back. So it never mattered when you factorize normal algebraic terms or numbers, whether you put it at the front or the back. Here it matters. Now that's correct. I times R is R and Q times R is QR. So that is correct now. Now to get R on its own, what I'm going to do is pre-multiply both sides by the inverse of I plus Q. So it looks like this written out in full. There we go. These cancel out because that's the definition of what the inverse is to give you the identity. So we're just left with R on its own, equal to I plus Q to the minus 1 times B. And that is exactly what the question asks us to do. Okay, then the question says, hence determine R given that P is that and Q is that. Okay, so R is going to be I plus Q, the inverse of that matrix there. Okay, so what's I plus Q? I plus Q is just that. Okay, so we've just got to add these two matrices here together. So you can see we get 2, 4, 1, 0. Normally when I read matrices, I go there, 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 and they're all there. So 2, 4, 1, 0. The inverse of that matrix times by P, which is 20, 14, 2, 1. Okay, cool, all good. Now, we know how to work out the matrix, the inverse of a 2 by 2 matrix now. So I'm going to do this quickly. The inverse of this matrix here is 1 over the determinant. Now the determinant here is 2 times 0 minus 1 times 4 is negative 4. The inverse is we're going to swap the 2 and 0, change the sign of these ones here. So that is our inverse matrix here. Now you could times by negative a quarter from there, but I'm going to multiply the matrices first. This thing, so 0 times 20 plus negative 4 times 2, negative 8. 0 times 14 plus negative 4 times 1, negative 4. For the bottom row, negative 1 and 2, negative 20 plus 4, negative 16. Negative 14 plus 2 is negative 12. So now I times everything by negative a quarter, and I get 2, 1, 4, 3. And that's my answer for what R is. In this last example now, we're going to extend this idea of inverse matrices to a 3 by 3 matrix. And you can go to 4 by 4, you can go sky's the limit. This is where you need your calculator. Working out the inverse of a 3 by 3 matrix is a little bit trickier beyond the course, but you can do it. So there's an option on a calculator to work out the inverse of a matrix. So in this case here, your calculator, I encourage you to grab it and work out. If you just do that to the power of negative 1, actually your calculator knows what you're talking about, and it will give you the inverse of that matrix. So your calculator will say something like this: 0.2, 0.20, negative 0.4, negative 0.41, 0.8, negative 0.2, negative 1. Just check that your calculator gives you that. Now, what's the connection between that and that equation there? Well, we can see that we can form a matrix based on this system of equations here. Okay, so let me show you how that's done. I'm going to form a matrix using the coefficients of x, y, and z in each one of these. So 3, 1, 1, my top row. In the next row, we've got 2, negative 1, negative 1. And the next row, we've got 2x plus y. So 2, 1, 0. Okay. 2, 1, 0. Now, we're going to multiply that by x, y, and z. So you notice if I do that, we've got a 3 by 3 matrix multiplied by a 3 by 1 matrix. These numbers are the same, so that's all good, and we're going to get a 3 by 1 matrix. And that is the answer: negative 1, negative 4, negative 5. Now, if you check that, you'll see 3, 1, 1, turn it on its side, 3x plus y plus z equals negative 1. You can see that that system of equations up here is now represented really nicely by this matrix down here. And as you can see from our work before, if we have ax equals b, the way to get x on its own, which in this case is this matrix here, we want to try and find the value of x, y, and z, is we multiply both sides by the inverse of A. In this case, x is the inverse of A times by B. So in this case, x, y, z is the inverse of A, I wrote up above, times by B, which is this matrix over here, -1, -4, -5. So this is where, again, we get our calculator out, multiply these matrices together, and you should get a 3x1 matrix that is -1, -3, and 5. And I encourage you to get your calculator out and check that that's true, that when you multiply this matrix here by -1, -4, 5, you get -1, -3, 5. So therefore x is -1, y is -3, z is 5. Cool.